Okay, in this episode, we are going to calculate transition probabilities. So, optical transition probabilities. So, when you absorb or emit light to go from one state of a quantum system to another. Due to radial coordinate weirdness, we're actually going to start with spectroscopy of a particle in a box. So go back to this system here. There's our familiar ground state wave function. The selection rules for particle in a box are you can only change the quantum number by odd numbers. So let's see if that's the case. This is the transition dipole integral here. The probability of the transition is actually equal to the square of this integral. But how do we calculate this integral here in our program? Well, it's just the initial wave function times the transition dipole moment, which is just x times some constant, times the final state wave function. So in order to do this, we actually need to be able to we can only display one wave function at a time. We need to be able to save a wave function for future calculations. So let's add a save button. Just going to use an OK button, type in save. I'm going to call it save, and then I'm going to get rid of the label. Maybe call it save wave function. So we're clear. That actually corresponds to that graph anyway. Okay, then we need to make it actually save the wave function. So we'll find it on our block diagram, move all this stuff out of the way. Give ourselves some room here, make a case structure. And if we press the save button, false, nothing happens, but if we press the save button, this happens. And we're going to save the wave function. We're just going to create an indicator for it. And we'll call that saved wave function. We're also going to save the energy level, because that will help us calculate transition energies. So make an indicator for that. Saved energy. Okay. That's all that needs to do. Clean it up a bit. Okay, so now we want to we want to calculate this integral right here. So we'll say our initial wave function is the one that we're currently but we'll say the initial one is this one. Doesn't matter the order in this case, but so anyway, let's grab this value, create property node value, then we can use its value in the program. We want to multiply that. Actually, we're going to do 3 multiplications here, so let's actually just use a compound arithmetic. Make sure we click on the plus, change it to a multiply. Multiply 3 numbers at the same time. The saved wave function. The wave function that we're currently calculating, that's currently displayed up there. And the x values. That's the transition dipole moment. Is the x value times the charge. And that is this times this times this. The integral means we need to sum this. And then we want to square that result, just because sometimes that can be negative. We have our transition probability. Okay. Let's also make it so that when we save our wave function, we display that on the same graph as this wave function we're currently calculating, just so we know if we have something saved and what we have saved and so forth. So let's make a bundle. We'll get our saved wave function up here too. Get our x values. That's our y value. Build an array, and we'll put both of these wave functions on here. And let's see if this is working here. So let's save that one, and then find the next state. So that's at like, what is it, 500 or is it? I think it's like 500. There we go. Okay, so there we have a probability. Let's organize all this stuff here. This is the same units. This we don't really need to look at. Here's our transition probability. Okay, so, well, that is a non-zero number. But how much bigger is it than a forbidden transition? Let's keep shifting to find out. Well, it's not changing. So if I save that, oh, there we go. I hadn't actually gone to the next state. There is the n equals 3 state. So that would be a delta n of 2. That is forbidden. You can see that number is essentially 0. Some number times 10 to the negative 26 is just an incredibly small number. If we keep shifting again, the next transition is non-zero, but it's less intense than that first transition, which is experimentally true as well. Cool, seems to be working. You could also, what you can do is you can start at the n equals 2 state and then see if you can go plus or minus 1 here. That's the same state. There we go. That's allowed. But if we go one more, it should be forbidden. And it is. Okay, so that is working. Now, the atom is different. So remember, for the atom, what we're actually calculating is this. So if we take this times another wave function times this times transition dipole moment times the Jacobian factor of r, we're going to get, you know, r to the 4th or whatever here. But actually, since we want to divide our solution by r to get the radial wave function, we need to divide our initial wave function by r, we need to divide our final wave function by r, but then we need to multiply by r for the transition dipole moment, we need to multiply by r for Jacobian. That actually all cancels itself out. So all you have to do for the atom, even though you're technically using the same integral, is just multiply the initial and final wave functions and take that integral. So I'm going to do something a little tricky here. let's see, what's the best way to do this? I'm going to take my x values here, and I'm going to make it so that when we're on the atom case specifically, we're not actually multiplying by the x values, but we're just multiplying by an array of all ones. So how do we do that? Well, we'll put in a case here where this is maybe what we need to do actually is make this a divide. So if we divide this by itself, it'll just be 1. Although we are going to have a divide by 0 error again. Okay. Let's reroute our plan again. Let's copy our x values, actually. If this is the atomic case, we're going to initialize an array of size equal to our number of points. Which I guess I can just grab here. And it's all 1s, and so that'll just come out and multiply by 1 there. If we are anything else, we're going to take our x values and use those instead. That should work. Now, instead of having to wire every single frame of this to the x values, what you can do is you can just do right-click, use default if unwired. So that means, like, for the well case, this is currently unwired. That's fine. It will use the value from this default case. And I think that should work, but I'm just going to kind of connect it anyway, just because I think it's easier to read. But if we ever forget to do it, it will use that default. Okay, let's just make sure that still works for our box, actually, since we just changed something. So we'll go back to shift of 0, save that, and then we'll start shifting up to where our first state is there. Yeah, that's the same number we had before. That's still forbidden. Okay, so that's still working. Does our atom work? Okay, for the atom, we need to go from like 1 to 15. Let's go down to the 1s orbital. That's a shift of negative 200,000-ish. Here we go. So we've saved our 1s there. And now let's shift up to our 2s. Will that be an allowed transition? No, you cannot go from an s orbital to an s orbital. That is just as we predict theoretically. If you absorb a photon has 1 unit of angular momentum. You have to change the angular momentum of your atom because angular momentum has to be conserved. So you cannot go from an s to an s orbital with an optical transition. Can you go from an s to a p orbital? Yes, you can. Just as theory predicts as well. And you can go to any of the p orbitals. Here's the 3p, although we're cutting it off. We need to increase our x range. And do remember, when you increase your range, you need to go back and save your initial wave function again, because it's been saved with the wrong number of points. So, so let's go back to S. Go back to, there we go, there's our 1s. Go back to P. There's our 2P allowed. Oops. There's our 3P also allowed, but less intense. And that's exactly what you expect as well. There is less overlap between the 1s and the 3p orbital than there is between the 1s and the 2p orbital. So that's pretty cool. Okay, selection rules and so forth, correctly predicted here. One last thing. Transition wavelength. Very important too. Here's our saved energy. We want to take our initial state minus our final state and actually, let's see, property node, let's get the value here. Actually, it doesn't really matter which way we subtract, because if we're doing emission or absorption, the signs are going to be opposite here. So let's just take the absolute value so that we're safe either way. Take the absolute value of the differences between the energies of the two states, the one we saved and the one we're currently looking at. That's going to give us a difference in energy in inverse centimeters. We want to convert that to nanometers, which should be 1e to the 7 divided by the number. And transition wavelength in nanometers. Cool, 121 nanometers. That might be right. The easier ones to compare are the Balmer series, which are the ones that don't actually start from the ground state of hydrogen. They start from the n equals 2. So let's check that. Starting at, okay, that's the 2s. Then going to the 3p, for instance. 656.449 nanometers. That is the red transition of hydrogen that you will have seen in the atomic lamps. And I will make you figure out where the rest of the transitions come from. So that's how you do simulate spectroscopy with LabVIEW. Now you know where each peak will appear on the x-axis of a spectrum, and also what its intensity will be.